So it's just e to the minus k times k minus 1 divided by 2 times 1 over 2n, but I'm going to bring the n down as well. Okay. So now recall that we say a random variable t is exponentially distributed with rate parameter lambda. This means the probability that t more than t, so this is, this is not the distribution function, it's 1 minus the distribution function, right? So then we just do e to the minus lambda t. So I'm just rewritten the distribution function this way. So for me, this makes sense because now I mentioned what is the probability that some random time is bigger than some fixed time, right? So what is the probability that k lineages remain distinct for a while? So and then the other thing about the exponential random variable, the expectation is 1 over the rate parameter, right? So this is just recall. So we're almost done. So now, by letting n approach infinity, so the population size is getting larger, and expressing time in terms of 2n generations, right? So this is our rescale time. So formally, we're letting our new units of time lowercase t equal n divided by 2n, right? Because n is my number of generations I wait, right? My probability is in terms of the little n. So now I'm letting t be n over 2n because 1 over 2n is my unit 1 now. So once I do this, then we get the following. At the time to the first coalescence event, when at least a pair of the k guys merge for exactly 1. So we go from k lineages to k minus 1 lineages. So this is just a nice word for choosing same ancestor. Is exponential random variable with rate k times k minus 1 over 2. Random variable. So that's the basic. It simply falls out of this, right? This approximation of the exponential, right? 1 minus x. And if you look at it, I'm just saying probability that the random variable is greater than t is this, because it has this form. So now I just have to rewrite this as my new t, right? N over 2n. So that's why I rescale time in units of 2n. I'm done. I have already an exponential random variable with rate k, k minus 1 over 2.
Where exactly do you use that when you let big n go to infinity?
Well, because we need this is the argument for big N going to infinity, right?
Okay.
Like Because this, remember, what was that thing?
Exponent.
Yeah, because we can only do this when x is small.
Yeah.
So the n goes to infinity. Means this term gets small, so then we can do 1 over tiny x thingy. Good. And then, so what does all this mean? Thus, k lineages coalesce to k minus 1 lineages at rate k times k minus 1 over 2. So this uses the continuous time Markov chain terminology. Okay. So that's the end of proof. So let's make a little picture of how this is supposed to be looking, and then define the state space of the Markov chain more carefully. Oh my goodness, okay, we still have half hour, right? So how do you guys find all this? Is this boring or more interesting?
I think it's interesting. Just coming back to the big and going to infinity there, for this in application, it's just, I think, sufficient to let 2n be sufficiently larger than little n, right?
Yeah.
And where the heuristics
I think, yeah, I mean, 10,000 is like way, right? Because all you really have to just think is, this is, this k times k minus 1 over 2 divided by 2n. I mean, that should be small, right? That's so it's really up to this 1 minus x being approximated by e to the minus x. Yeah. Yeah, well, that basically breaks down when k equals to n. That's the case of some rich Gulf countries right now. But this is, again, when your sampling strategy is not random, like Icelandic population, same problem. You cannot do this theory. I mean, but yeah, once you go through the pedigree and you will reach a stage where you will still have samples, and then you can apply coalescence theory. Because you don't know anything about pedigrees. But that's already close to research problems. Okay, so let's look at the what does this mean in a genealogical sense now? So the limit of genealogies in theorem 4 is what's called the coalescent. So let's get some insight into this. Let capital P sub j be the first time with j lineages. Okay, so then we have the following picture. have present, so now, and then I take some samples. So I have like 2n individuals scattered here, and I just take one guy, another guy. So I'm going to call this guy 1, this guy 2, some other guy here 3, and say another guy here 4, and another guy here 5. Right? So these are my samples, and of course there's several of them, right? So I give them some canonical labels, 6, 7, 8, up through 2n. So I only took 5 of them at random, and then what I'm interested in is what happens to their ancestries. So I track their ancestry. So, you know, in discrete time, there is the next generation and so on, right? There's a lot of, so I can imagine lots of little arrows like a group, right, going back. But now I'm looking at continuous time, in rescale time. Now my unit 1 is already 2n generations. I'm not drawing all those discrete things anymore. It's too much. So all that matters to me is whether they've collided or not. You know, they coalesced or not. So I'm going to track this. So this remained distinct up to here. And then there was a coalescence event. So they coalesced and formed this ancestral state. No. And this happened at time, so I'm going to keep track of time here now. So this happens at time capital T5. Sorry. So T5 is when we first found the system, because we did the sampling, we found 5 distinct guys. And this is T4, capital T4. So that's the first time we are finding, and this guy keeps going up, this guy keeps going up and up. So at this point, T4, we have 1, 2, this is the new, and 3 and 4. 4 distinct lineages, right? And I run this further back, let's say here, there's another coalescence event, let's say. And this is when I find T3, capital T3. Okay, and this keeps going. And let's say at some point here, this is still going. I find T2, and this keeps going. And some other point here, I have my T1 and T2. Ooh, yeah. So then this is what we've been studying, right? This is lowercase t2, right? That's the amount of time that there are 2 distinct lineages. And this is lowercase t3 and so on. Lowercase t3, lowercase t4, and lowercase t5, right? These are what we studied in the theory. So this is now called a realization. So this is basically a sample of our random structure, right? It has some tree shape and branch lengths. So it's a realization of the coalescence. For a sample of size 5, drawn randomly from a large population. Of size 2. Okay. So this is basically what Kingman did. So Kingman produced this Markov chain, which we're still about to define. What we focused on is just the branch lengths now. How long will there be exactly 5 lineages? How long will there be exactly 4, and so on? That's what we've done. So, so before we get into the topology and the discrete structures, the state space of the Markov chain, let's ask a simple question. What is the expected coalescence time? Right? So as I said, the lowercase t's are also being used as a random variable just because be in sync with Rick's book. And it is convenient because the capital T's are sums of the lowercase t's. So E sub T2 is interestingly what? So you know that T2 is an exponentially distributed random variable, right? What is its rate parameter?
Number of design?
Yeah, so its rate is 2 times 2 minus 1 over 2, right? Which is 1, right? So, and then the mean is 1 over the rate, right? So 1 over 1 is also 1. So the expected time you wait, you know, with 2 lineages is 1 in this rescale time units. So it's roughly of 2n generations in the discrete units. So now, what about E expectation of T3? So it's 1 over the rate, right? Rate is what? 3 times 3 minus 1 over 2, right? So this is 2, so it's 1 over 3. And similarly, E of T4 is 1 over 6, and E of T5 is 1 over 10. So I've just drawn a realization, right? So this was just a realization of an exponential random variable with rate 5 choose 2. But its expectation is 1 over 10, right? So on average, this branch length is 1/10 of this branch length, right? So this is somewhat surprising in a way, and maybe not. So what Kingman's coalescent is telling us is that if you have lots and lots of samples, the expected time to find an ancestor grows very, very quickly down, right? With the sample size, it's quadratically. Which makes sense because, you know, if you have lots of people, then the chance that at least one of them finds an ancestor is very high. And then if you have 2 guys here, you know, you still have 2n generations in the discrete model under the hood, right? We're looking at the limiting approximation of the discrete thing. So it'll on average take a very long time for 2 random guys to find an ancestor. That's what this is. So it's not intuitively too difficult, right? And that's coming from the Wright-Fisher model and Mixia and everything. Okay, so then the next thing, so all of this is because expectation of tk, this is 2 over k times k minus 1. Okay, so then, so T1 is basically time, right? That's the top one. So T1 goes, it measures from here 0 to T1, right? So that's the time of the occurrence of the so-called most recent common ancestor. Most recent common ancestor of the sample, right? Or MRC of the sample size 5, right? And that is simply the sum of the lowercase t's. You know, remember n lineages and minus 1 lineages all the way to 3 lineages and 2 lineages. So clearly the expectation of T1, so remember this is one of the properties of expectations, it's a linear operator, we can take the expectation inside the sum. So this is just the expectation of the sum of all the Ti's. Right? All these K. And this is just summation 2 over K times K minus 1. That's the mean of each one. And I don't know. We'll just break this into each piece. And yeah, and then just do the sum separately, and you will see this will just be 2 times 1 minus 1 over n. And this goes to 2, or as the sample size goes to infinity, slower than the population size. Okay, so for large sample size, this is very close to 2. Right. Okay.
So for example, in a population of 1,000 people, if this is big enough, there will be like 2,000 generations. Or
so I mean, let's work in continuous time now, right? In this rescale time. So I mean, I'm just saying, you know, if you just keep this as whatever number, it's roughly 2. So the point is, you know, say even 10. So 2 times 9 tenths. So it's roughly 2. Even for sample size 10 or 30, it's very close to 2. The time to the most recent common ancestor is 2 units in this rescale time, right? Which means because we're dividing time by 2n, it's actually 4n discrete generations is roughly how long you have to wait before you find a common ancestor of a large enough sample, right? So 30 or 100, little n is 100, capital N is 10,000. So the point is, it's quite a lot of time you wait until the whole sample finds a common ancestor. I mean, whatever it is. It's order n, right? That's Kingman coalescent. Almost. But now you notice that the expectation of T2 is equal to 1, right? So that's essentially half of this time is spent on waiting for the last coalescence event, which is roughly expectation of T1 divided by 2, right? So you spend half the time finding the last event. So I thought, let me outline the simulation. So this is basically one of the exercises for this for today, and then I'll formally define the finance the Markov chain. Well, maybe I'll formally define the Markov chain first. So let's see. Not have time otherwise. So here's so we have kind of all the basic pieces, right? You haven't seen the state space explicitly for the coalescent yet, but you know what the times are as the lineages become. Before we get into the state space, let's write down a simulation algorithm of how to produce realizations from the coalescent, and then the state space will become obvious. Okay. So what we're going to do is we're going to have exactly the same tree. So I'm not going to rewrite the tree. So what we're going to do is, so consider the tree. So let's label the internal nodes. Right. So I'm going to have this canonical labeling. I have 1, 2, 3, 4, 5. I've exhausted right. That's my sample size. The first node I find, this is an internal node. I'm going to label this guy 6. And then this is the next node I find. I'm going to label this internal node 7, this internal node 8, and this one 9. Okay. And because I will need to define other functions like whose ancestor and things like this. So I need the internal nodes labeled. So then what I'm going to do is introduce, I'm going to erase this stuff. So I'm going to introduce sets. So these are time events that we need to simulate, but also initially at this time, T5, there is a set I'm calling V sub 0. Okay, so this set is simply the set of all labels. Okay, so put everybody together, that's my set of labels. At the next time step, I'm going to call this V1. I have the following labels, right? So I still have 2, I still have 5 because that's the same label. And then I have still 3, but then 1 and 4 coalesced and became 6, right? So I'm going to keep my list of extent labels, or whatever the ancestral labels. So 2, 3, 5, 6, and so on, right? So this is V2, and V2 is 3, 6, 7. Right? 6 is here, 7 is here, 3 is still alone, and V3, right? Oops. 7, 6. What happens here? We have 7 and 8, right? Okay. And I'm done because I know here everything goes together. So that's sort of what I need for my simulation. There is another process I'm going to keep here. Okay. So initially, this is going to define for us the state space of the Markov chain. So actually, the Markov chain state space is on all the set partitions of 1, 2, 3 up to 1. So, so what are set partitions? Set partitions are just all the subsets of the set, right? So, we'll do set partition example here. So if I have just 1, 2, and 3, it's a tiny set. It has, so this is, one set partition is all of them separate, right? 1 by itself, 2 by itself, 3 by itself, oops, right? So this is this is everything together. There's only one block here, right? And here I have 3 blocks, each is by itself, right? So in my Markov chain, initially for this example, I'm actually starting here like this. 1 is by itself, or 3 is by itself, but I'm going to do it in this order. Right, so this is my this is my initial state, because everybody is on their own, okay? And then, the next step, what happens? 1 and 4 coalesce, right? We just relabel that as 6 for simulation purposes, or to have internal nodes on the tree structure. But the Markov chain basically throws these two things together. So 1 and 4 become a new set, right? And the rest, and remember these are sets, so the order in which I write this doesn't matter. And then 2 is by itself, 3 is by itself, 4 is by itself, and so on, right? Oops, 4 is already absorbed into there, 5 is by itself. You see, so there is a jump from, so think of this as a state, right? So we have a state, and there is a transition from this state to this state, okay? And of course, there is an arrow from here to not just this, right? There are 5 choose 2 possibilities, right? Because so the question is, how many collisions can I have? I can have 1 join with 2, 1 join with 3, 1 join with 4, 1 join with 5, right? So that's why you have k times k minus 1 possibilities, right? So initially I can take any one of them, so there's 5 of them, and then to choose the second one, there's 4 of them. So there'll be there'll be 10 choices, so there should be 10 arrows, right? 5 times 4 divided by 2 is 10, so there'll be 10 arrows pointing out of here, just to reach all the set partitions made up of 2 blocks. So this is block 1, this is, sorry, not 2 blocks, 4 blocks, 1, 2, 3, 4, yeah. Right, here we have 5 blocks, there's only one set partition of 1 through 5 with 5 blocks. This is the unique one, right? So it's in the bottom, but then there are 20 of them at this level that you can choose from. And so what Kingman's coalescent does is it chooses each of these 20 with equal probability, 1 over 20, okay? And but then the rate at which the the alarm clock goes off is 20.
Is it 20 or 10?
Is it 10? Oh yeah, sorry, you're right, 10. Thanks. Yeah, I forgot the division by 2. Yeah. So there's 10 of them, right? And then so it'll make a transition with probability 1 over 10 at this rate, which is 10. So this cancels. So at rate 1, it'll go to one of these 10 possible transitions. That's how you think about solve. And then it continues like this, right? And then there's there's a lot of partitions with 3 blocks and 2 blocks. And then the last one is the final partition. So this is an absorbing state. So everything will be in 1 block. So there's only one of this guy, right? So everything will come here. So that's how Kingman basically developed the state space. And so now you can understand why the continuous time structures and the discrete time structures are nicely put together. Like this was his major achievement, one probability model for everything. So in this case, yeah, you can just write down everything, because this is just so this is the 2 block stuff, 1, 3, and 2 by itself, and what am I using? 2 and 3, and 1 by itself, right? So it'll start from here and choose one of these with equal probability, 1/3, 1/3, 1/3, hit it with rate 3. So at rate 1, it'll go to each of these, and then it will just choose this one with probably one, say grade 1, so it will be coming here with. So this is this state transition diagram for just 3 samples. Of course, this is easy to write down in general. So now let me quickly write down the simulation algorithm in the next 5 minutes, and then we can call it stopping point. So the input to the algorithm should be sample size. Okay, so there's a bunch of little bookkeeping that we have to do. So the input is going to be sample size n. And we're going to initialize some initialization steps. I mean, I'm not writing the exhaustive algorithm, right? So exercise. So we have to initialize this v set at time at 0, and then we also initialize this capital T as Tn to be 0. And then there's a loop, it's the main body, for k equals 0 on up to n minus 2. Do the following. So you pick I sub k and j sub k from vk uniformly at random, right? So this has to be 2 distinct ones, so you have to pick without replacement. And then v sub k plus 1 gets v sub k set minus ik jk. So remove the guys that you just picked, and then union that with the set n plus k plus 1. So I mean, all the stuff we did on set operations in Sage Math should be useful now, right? So that's how we get the vk plus 1s from the previous case. So and then you have to figure out how you want to represent the tree. There's many ways. You can do it just with lists or however you want. So in your data structure for the tree, you connect ik to n plus k plus 1 and jk to n plus k plus 1. So that's this is what I mean. So here I would like you to think about defining a function called ancestral function, anc. So what I mean is ancestor of ik is the integer n plus k plus 1. And the ancestor of jk is also n plus k plus 1. So I can ask what is the ancestor of 1 and should give me 6 and so on. That's useful on the road. And then there are the last 2 steps. And let lowercase t n minus k be exponential random variable with rate parameter n minus k choose 2. And the capital T n minus k minus 1. Let this get t sub n minus k and lowercase t n minus k. And you already know how to simulate from exponential random variable. So that's basically it. Yeah. I mean, another tip is maybe when you want to get, you may want to be able to get a branch of this tree. So this is a branch, so that'll always be. So you can always get the branch by, if you notice, every branch can be labeled by the integer that's below. So this branch will be called 8. This branch can be called 7. This can be called 2, 5, 1, 4, 6, and 2. Right? So you can have a unique labeling of each branch by the integer below it. So so you may want to have a branch function. All right, that's basically the simulation algorithm. So see if you can do this. When we come back, we'll continue with mutations and we'll give it to Dimitri.
1:30.
Yeah, 1:30.